We move now from the study of ethylene and the polymers that you can produce from ethylene to having a look at how structure relates to function. In other words, how does the makeup of these polymers affect the way that they behave, their physical properties, and what we can use them for. Now the syllabus is going to ask you to be able to do this. If you move down to the last bullet point, you can see that you're asked now to describe the uses of the polymers made from the above monomers in terms of their properties. So you need to know the properties of the polymers and how those properties relate to the uses of the polymers. Let's have a look now. We often call this the relationship between structure and function. Now the structures of polyethylene, PVC and polystyrene, the 3-addition polymers that you need to know, they actually tell us a lot about their function. In other words, an examination of how they're made up gives us a hint as to what we might use them for in real life. So for example, polyethylene is good for plastic bags, but PVC is perfect for guttering and pipes. Why is this so? Well, we need to know something of their structure. So you as the HSC chemist needs to be able to relate a polymer's structure to its function and then discuss why it's suitable or unsuitable for certain uses. Now the first property of certain polymers that we will look at is called chain branching. Now chain branching has already been introduced, and we know that low density polyethylene exhibits side chain branching. So the presence of a side chain branch reduces the density of the final polymer. So again, schematic representations on the right hand side of screen, you can see low density polyethylene is low in density because it has side chain branching. Now, any polymer without side chain branching is going to have a high density because it's able to pack neighbouring molecules closely together. We call these types of polymers crystalline polymers. They have high melting and boiling points simply because they have a close proximity between neighbouring molecules that make up the overall polymer. Remember the word crystalline from your preliminary studies, and it was used to describe network covalent lattices such as diamond, or an ionic lattice such as sodium chloride, where we have an ordered array of closely packed atoms that are crystalline. That's true also of any polymer that does not have side chain branching. It packs together in a very orderly and stable fashion. So these tend to be hard, rigid, inflexible and tough, in the same way that those covalent lattices from the preliminary course exhibited these properties. Why? They're so tightly packed together, they're so orderly that they exhibit these hard, tough, inflexible properties. So the structure relates to their function. An example would be some of the polymers that might be used in the plastics industry to make something like that white bucket you can see on screen. A hard, rigid, inflexible, tough polymer due to the closely packed polymer strands that don't have any side chain branching. Polymers with chain branching have lower densities. Now this is because they're unable to pack closely together. We call them non-crystalline or amorphous, and therefore they have low melting points and boiling points. This is because the intermolecular forces are not as strong due to the less tightly packed molecules within the overall polymer. So these polymers with chain branching tend to have low melting points and boiling points, and therefore they're also soft, flexible and clingy. An example would be, say, cling wrap, or a disposable plastic glove where you have flexible, thin, malleable, soft polymer resulting from that presence of side chain branching that has lowered its density. Now, there's a phenomenon known as chain stiffening. The side chains in LDPE, low density polyethylene, are long hydrocarbon alkyl groups. Remember, these are very stable and unreactive. Now, chemically speaking, these side chains tend to be rather slippery in nature. They don't have a strong intermolecular force for other side chains. It's just a dispersion force. And they tend to flop around. They don't really cling to one another, and this explains that clingy, slippery nature of low-density polyethylene. However, if you have a side chain branch of another nature, such as the benzene ring of polystyrene or the chlorine atom of PVC, we actually see that these side chain branches have the reverse effect. You see, the chlorine atom and the benzene ring are much bigger and more numerous than the CH3 group of, say, polyethylene. What that means is that the side chain branches on PVC, for example, have a very different nature to the side chain branches on low density polyethylene. These side chain branches, the benzene ring and the chlorine atom, are unable to flop around, to slide past one another. They actually line up in a very rigid and orderly way that starts to give a very different function according to this structure. Let's take, for example, polyvinyl chloride and polystyrene. These two polymers exhibit a very hard, stiff, rigid type of property. Now, you may be confused because we're used to associating polystyrene with packaging or styrofoam cups, and we all know that it's possible to bite into a polystyrene cup and leave your teeth marks indented within the polymer. Now, the reason that you can do this is because during the production of polystyrene, an inert gas is bubbled through the polymer as it's produced, which leaves millions of tiny little air pockets. When you apply pressure to this, you're not compressing the polymer itself, you're actually compressing those air pockets. That's why you can leave an indentation. But the PVC itself is incredibly strong and stiff and resistant to breakdown. Therefore, you can only leave your mark or tear it, but you'll never bite right through it as it's an incredibly hard polymer. So don't be confused about the softness of polystyrene. It's actually incredibly hard. It's the presence of gas bubbles in the polymer that makes it appear soft. So we can see therefore that PVC and polystyrene are the only polymers we study that have chain stiffening. This chain stiffening phenomenon is the orderly array of the side chains that are unable to slip past one another and provide a slippery or floppy kind of polymer. Rather, the side chains lock together and therefore stiffen the overall polymer, making it very hard, rigid and tough. Low density polyethylene has chain branching, but because the chains are not stiff, we end up with a much more flexible, malleable polymer. Now, some of the other properties that you need to examine in these polymers are as follows. All three polymers are insoluble. This is because of their high molecular weight. They're big molecules. Remember, the bigger the molecule, the less likely it is to dissolve. They don't have any polarity. So a solvent like water that is polar will have no affinity for the non-polar nature of these molecules, and they lack hydrogen bonding groups. There's nowhere where you have a sufficient dipole in action, such as a fluorine, an oxygen, or a nitrogen atom, hogging those electrons, so you do not have the ability for hydrogen bonding to occur. So they're insoluble. They're also very stable due to their carbon-carbon bonds and their carbon-hydrogen bonds. So once they've been produced, they're incredibly unreactive and stable. One exception to this rule is PVC. Now, polyvinyl chloride, we know, has a chlorine atom, and the carbon-chlorine bond is susceptible to UV attack. So if you place PVC piping outside, over time the UV light that we receive from the sun is able to attack the bonds on the chlorine atom and therefore break those apart so that the side chain of chlorine slowly disintegrates and disappears. Now, if you take that side chain away, you're reducing the overall stiffness of that particular polymer, and you'll notice that any PVC pipes that are left out in the sun over time will crack very easily, become brittle, and after only a few years are useless. Therefore, if PVC is used outside, you'll find that it's been painted to protect it from UV attack, and we tend to now associate PVC piping with plumbing and areas underground where there's no UV light to attack it. The other problem with PVC breakdown is that the chlorine atom will usually combine with some hydrogen and form hydrogen chloride, which of course in aqueous solution is a strong acid, which can then go on and cause issues by lowering the pH of the surrounding environment. Now, it's important that you can summarise the uses of different polymers. This is available in your textbook, but quickly, I've summarised them here for you. Low-density polyethylene has chain branching, but it does not have chain stiffening. This means that it's low density with the presence of side chain branches that are not stiff, so therefore it's flexible and clingy, it's weak, has a low melting point. So it's good for things like cling wrap, shopping bags, squeeze bottles, those sorts of properties give it that kind of function. High density polyethylene does not have any chain branching, so therefore it can't have any chain stiffening, but because it packs together so closely, it now is rigid, stiff, hard, strong, and has a high melting point. So this is good for uses such as kitchen utensils, containers, wheelie bins, pipes, buckets. The chairs you sit on at SCAS are probably a form of polyethylene. PVC doesn't have a lot of chain branching, but the chain branches that it has are very stiff. So again, this is hard and stiff, and it's got a high melting point, but it's susceptible to UV light. So you tend to find this in drainage and sewer pipes, downpipes, window frames, anywhere that you need a rigid polymer that can be kept out of UV attack. Polystyrene, however, does not have a lot of chain branching, but the chains are exceptionally stiff. This means that it's a very hard, stiff polymer that's also resistant to UV light, so it can be used outside, and you tend to find polystyrene in tool handles, CD cases, but also packaging and disposable cups. So there is a table that relates the properties of a polymer to the uses or function of that particular polymer. A quick note on PVC. You know that PVC has a chlorine atom bonded to a carbon atom. That means that it's highly electronegative, so there's a dipole formed around this bond. If you think about it, chlorine is much more electronegative than carbon, so as they share electrons, the electrons will spend more time around the chlorine atom than the carbon. This yields a dipole. Now, because of the dipole, PVC exhibits a strong intermolecular force which adds to its overall stiffness. Due to the geometry of this dipole, it's not sufficient to allow a polar solvent like water to dissolve it, so it's still insoluble, but as an intermolecular force, you not only have dispersion forces present and chain stiffening, but you've got dipole-dipole forces present within the molecule, which makes the overall polymer incredibly tough, strong, rigid, and resistant to attack. Some of the polymer uses are listed for you on table 1.2 in your text, and you can study that for yourselves. Now, there are some exercises that you need to be able to do on page 20 to 23. Exercises 20 to 23 on page 21. Worksheet 3 from Conquering Chemistry Blackline Masters, and there's an example of the questions from your text.